Welcome. In this slide presentation, we're going to look at how we can solve systems of equations. We're actually going to look at several different ways to do this, but we're going to start off with the one that kind of gives us the most visual idea of what we're doing here, which is using graphing to do so. So first of all, let's just talk about what is a system of equations. A system of equations is when we have at least two or more equations and we're looking for any common solutions they may or may not share. So in other words, we've got different equations representing different relationships between x and y, and we can even have more than two variables. Sometimes we solve systems of equations with three variables. But regardless, the idea is we want to see, do these relations, these functions, these equations, do they have any common solutions, which would be common ordered pairs in our case of looking at situations with two variables. Okay, so thinking about this, and we have of course been working with linear equations here. There's basically three possibilities. If we have two linear equations, and we can look at these from a graphing standpoint, which is why this is kind of the most helpful, looking at them in terms of graphing. When we talk about shared solutions, of course, the points on our lines are our collection of solutions for each relation. So where these lines intersect would represent the solution that they share, right? The points on the line represent all the solutions for each equation, and so any points that they share would be points where they would cross each other and have a similar point. So if we have two lines, it's possible that we have one solution to our system. And when we have at least one solution to a system, we say it's consistent. So this would be a case where we have a consistent system, and that system has a solution. And these are two independent lines. So for this, we would say those three things. There's a solution. That solution would be the xy point where they're meeting. Because they have at least one solution, they are consistent, and they are independent of each other, meaning they are two different lines. The other possibility is that when we graph our two lines, we find that they actually do not cross each other. This would be, of course, if they are parallel to each other. And if they're parallel, that means they're never going to cross. The only time we have two parallel lines is if their slopes are the same. Okay? If two lines have the same slope, they are rising and running at the same direction. And so generally, they're not going to cross anywhere. And so in this case, since the definition of a solution here would be where they are crossing, we would say there is no solution for this type of system. These are inconsistent because there is no solution, but they are separate lines, so we still say they are independent of each other. Okay. And generally, we can use the circle with the line through it to kind of represent the idea of the empty set of solutions, no particular solutions. All right, then we come to our last possibility. When we graph our equations, sometimes what we discover is, in actuality, the two equations cross each other. In fact, they cross each other at every point because they represent the same equations. In this case, we have infinite solutions. I would say infinite solutions. Because remember, the solutions are the points that they share. And if they're the same line, they share every single point along the line itself. And so they are consistent. They have at least one solution. But they are not independent of each other. They're actually dependent systems. Because think of it as two lines. They're kind of depending on each other because they're sitting on top of each other. So those are the three scenarios that we kind of run into. Graphing-wise, we can literally see that when we look at algebraic methodologies of solving systems of equations. In the next couple videos, we're going to look at what type of weird situation we run into where we realize it's one of these two sort of not as common, but do happen once in a while situations. Okay, so looking at this, let's do an example here. And we're given a system. So we're given two equations here. And we're being asked to find the solution. So I'm going to go ahead and graph these. Now for this first one, I'm going to just use a table to do so. Remembering there are many different ways of solving and graphing equations. And sometimes one method is a little more preferred than the others. These are both in slope-intercept form. And so I could use the slope and the y-intercept to do so. But I like to remind us, we can also just go back and plug in values for x and figure out what the y's are. The main idea of graphing is when it comes to lines, you've got to find at least 2 points that they cross through. So I'm going to plug in 3 values for x, -2. So if I start out with -2, that's 2 times -2 plus 3. So that's -4 plus 3, which is -1. So -2, -1 is a solution. Plugging in 0 always eliminates, since it goes here for x, it's going to eliminate the 2, so then we just have 2 times 0, which is 0 plus 3. So 0, 3 is another point. And I know that also because 3 is the y-intercept part there. And then if we have +2, that's y equal to 2 times +2 plus 3. So this is no longer -4, but rather +4 plus 3, which is going to give me 7. All right, so I'm going to go ahead and just plot those points out. -2, -1 would give me a point right here. 0, 3 would give me a point here. And then 2, 7 is going to give me a point way up here. And then we'll use our straight edge and connect these points. It's really important that you get these correct as far as nice and straight as you're graphing them. Because what we're looking for is a specific point where they cross. So be really careful as you draw these. Of course, you'll be doing a lot of this online, which is a little helpful. But doing it on paper, you got to be really careful. All right. For the other equation, I'm going to do this one in red. I'm going to use the y-intercept and the slope. So my slope I know is -1/2. So that's -1 over +2 or +1 over -2. Both of those equal -1/2. And the y-intercept is 0, -2, because there's that subtraction there in front of 2. So I know that this is one of the points. And with the slope of -1/2, that's going to mean I'm going to move, if I move up, I'm going to move to the left 2 units. It looks like I may have already found a point here. Moved up 1 and back 2. Remember, I can also move down 1 and to the right 2, but you see all of these points kind of lining up here. And when I moved like that, it looks like I actually found the solution here. The solution was at -2, -1. This should be the value, the point that makes both equations true at the same time. And we can check that. Well, actually, we have that here. -2, -1 was this point here. Let's try plugging it into the other equation. So if I plug -2 in, that's -1/2 times -2, which gives me let's see, negative 1/2 times 2. Do I have that right? Negative 2, negative 1. Yeah. Oh, okay. I'm sorry. Yes. So this is 2 over 1. So we're going to go 2 times. So our 2's cancel out. That leaves me with negative 1. But it's negative times negative. So positive 1 minus 2, which is negative 1. So it looks like negative 2, negative 1 is a solution to both systems. Let's go to another example here. Here we're going to find the solution for this system. Again, they're both in slope-intercept form. So I'm going to use the slope and the y-intercept here. So the slope is 2 and the y-intercept is 7, which on our graph would be up here. And the slope being 2, this is kind of an important point, that's positive 2, so we can think of it as positive 2 over positive 1, but we can also think of it as negative 2 over negative 1. Negative divided by a negative is also positive 2. So, the reason why I might want to do the other one is because I'm already at the top of my graph here, right? If I want to go up 2 and to the right one, that's going to take me off the particular graph I have. But in this case, if I go down 2 and to the left one, that also will give me points. Down 2 to the left one, down 2 to the left one. And so here we have, okay, that was a terrible line. This is why you should always use a straight edge. Mine was not that straight. And now we're going to go to the other one. The other one was y equal to 3x plus 1. I'm going to go ahead and do a table for this just for fun. Do something a little bit different. I like to stick with some consistent points that I generally plug in. So plugging in negative 2 for x, that gives me 3 times negative 2 plus 1. So that's negative 6 plus 1, which is negative 5. And then 0, of course, is going to give me 1. And then if we plug in positive 2, that gives me 6 plus 1, which is 7. Okay, so positive 2, 7. Oops, let's go ahead and do a different color here. 0 and 1. And then we had negative 2, negative 5. Okay. Well, in this case, you'll notice that my graph isn't big enough. Somewhere up here, they don't have the same slope, so I know they're not parallel, but somewhere up here, they're going to cross. So it kind of looks like it might happen around 3 or possibly 4. So what we're going to look at in the next couple sections is, hey, if the graphing isn't working, one of the other sort of downsides we have with graphing is, what if they intersect at a fractional value, right? What if their solution involves fractions? Can you really discern fractions on most graphing? Well, maybe with technology, yes, but in general, no. So there's some real limitations to using graphing. In this particular case, I want you to, looking at these two, notice that they're both set equal to y, as they're both in slope-intercept form. So I'm going to use just a quick alternative way of solving this. If I set them equal to each other, since they're both equal to y, we can set 2x plus 7 equal to 3x plus 1 and find the x value that represents a shared point for them, a shared y output. And getting the x's to one side, this is a really, this method that I'm using here is the substitution method, which we're going to look at in the next section. Subtract 1, we see at x equal to 6, we're going to have a shared common outcome. In other words, I'm going to get the same y. Remember, y was equal to this, and y was equal to this. So by setting them equal to each other, we're really substituting y or the expression for y in for y in the other equation. Well, how can I find the ordered pair, right? Because the solution is always an ordered pair. Well, plug 6 into one of those equations. And in fact, either one you pick, we should get the same result. If I use the first one, that's 2 times x, so 2 times 6 plus 7. So that's 12 plus 7, which is 19. Do we get the same thing with the other? Well, that's 3 times 6 plus 1, so that's 18 plus 1, which is 19 again. So 619 is our solution here, and unfortunately with our graphing, we would have had a hard time finding that. So this is an opportunity for you to practice some of your graphing and getting acquainted with solving systems of equations. In the next couple videos, we're going to look at doing it using substitution and then also elimination or addition.